Hi everyone. So today I'm going to record a solution for weekly contest of 364 of LeetCode. So I will go in fast mode. So I will not recommend the beginners to watch this video. If you have some knowledge about data structures and algorithm, then you can look this video for your reference, just for your reference. Okay, so let's move to the first problem. The problem says like uh, we break down the problem. The problem is simply like there is a string of 0 1, so we have to make the maximum number possible. So maximum number, like what can be the maximum number? So if you look at, then all ones should be uh, most significant bit side, and all zeros should be lowest significant bit side, and the number should be odd. So the last digit in binary representation should be 1. So like the question simplified to like what we will do, we will shift all these ones into this side, all these one uh, into this side, and all zeros into right side. Okay, so this this one we will move to here. This will become odd numbers and the maximum possible. Why this is happening? Uh, the maximum possible number will be like this, but there is a one condition that the number should be odd. So we want to move one digit to this side. Uh, which bit we want to move? So if we will move these bits, uh, we will lose more because these bits have two power I kind of thing. Contribution in the whole numbers, and let's say this is the 2 power I, then this is will be I plus 1. So 2 power I plus 1 will be always greater than 2 power I. So that's why this is happening. Okay, so we will move this lower significant bit uh, in this range to the rightmost side, means least significant position. So this will be our solution. So I have done that thing. So I have first sort all the numbers in reverse order, and then move the first that bit in the last position. So, okay, so this uh, I have done like I have broken here, and then I have set the last number here. Okay, so that's the hold up. Now coming to second problem. So the second problem is kind of brute force we can do. So you have to like make the towers. If you read the question, you have to make the like, towers in this fashion. So like at the ith position, there is maximum height, and uh, this side is decreasing in this side. So you have to find like the sum of all these heights that can be done. So you have to maximize the sum of these heights. Okay, so what you can do, uh, the first intuition will be like going over each index and checking that if it is the maximum, then what will be the height, the total sum of height. So this is the like solution we are doing here. Okay, so the condition are like the max height you have given, and the height you will choose will be less than the max height. Okay, it will not greater than the max height, and it will be always greater than 1. Uh, okay, so what you can do, you can uh, just taking each index and then trying to make this index as the maximum height. and then decreasing all others left hand side and right hand side height is. Uh, with that, I think that will be a solution. So what I have done, uh, I have declared the answer for taking the maximum of answers, and then here I am doing like I am assuming this is the max side. Then I am going to left side. So I am decreasing the height. Here I am decreasing the height. So I am taking minimum of next right height and then the current right height. So both I have taken minimum and then this I have added into that. Okay. And same goes for right side. So here I am taking minimum and then adding it to 10 by 10. And then finally taking the maximum all answer. So this is kind of brute force solution. So that constant is like that, you can do this. So this completes our code. Now coming to the third. So here we have to like this question is same, but the constant is bigger. Okay. So the max height is now order of 10 power 5. So we cannot apply that checking for each height and so here also we are going to check for each height, but the optimization will be how we are going to make how we are going to calculate the answer for that height. Okay. Uh, so basically, uh, let's say the question is like this. So let's say we have some kind of prefix and we have some kind of suffix. Okay? Prefix and suffix. So let's say talk about prefix and then you will get a what is the suffix. Okay. So the prefix will be like this. Okay. So let's say we have answer for up to ith. We have already calculated up to ith. Okay. So what the prefix will says? It says that if what will be the answer prefix I will store what is the sum began. What is the sum uh, from left side if ith is the max, is the max. Okay, so you are making the ith one the biggest one, and then there will be some kind of uh, decreasing kind of. So the ith one will be the maximum one. Then this will go like this. So this will be like this kind of decreasing. So now, if we calculate this, then uh, our half part is done. Okay. So how I am going to calculate that? Say related one. Okay. Okay, so think about like this. Okay. So you are at ith position and you want to calculate that AI is the maximum height. And if AI is the maximum height, then what will be the sum from left side? So now think like this that uh, if this I minus one number is greater than AI, then this side can be a other situation. Okay. So there will be two cases. Let's say this side AI minus one is A of I minus 1 is less than A of I. Then what will happen? In this case, we are done. Okay, so we will calculate the answer will be prefix of I is equal to prefix of I minus 1 plus AI. Why? Because The I minus one already have ensured that all these number are decreasing order. Okay, and the I we will in I we will simply add. So this will still form a increasing order. Okay. Uh, if it is not, then there might be case that I minus two will be less than AI. Okay. Here what happened here? AI minus one is greater than or equals to AI. Or we can put equal to here and greater than. So now it is greater than, okay. So if it is greater than, then we will move to I minus 2 index. Okay. So if it is greater than, we will move to I minus 2 index. Now I minus 2 we will check that what is I minus 2. So if it is also less than, then we will done like this only. We will prefix of I will be prefix of I minus 2 plus 2 times A of I, because I minus 2 we can I minus 1 will become is greater than, so we will make up to I up to I height, ith height, okay, and from this side it will be kind of decreasing. Okay? So now what I'm going to do, like this it will continue up to we not get the ith height, okay, means let's say we will continue up to j, so the condition will be a of j should be greater than or a of I, where we will break. So the answer will be, updation will be like this: prefix of I is equal to prefix of j, not j, uh, it should be greater than, sorry, prefix of j, prefix of plus how many count is this, so it will be j minus I minus j, okay, uh, I minus j into a of I. So this will be our updation. So this will form all the prefix. Similarly, the suffix will also be formed. The suffix will be from right side to left side. We will move and we will update. Okay. So what I have done, I have make a prefix suffix and then one vector, and then I am doing the same thing in different way. So I'm doing like in this vector, we are pushing. First, we will push this number here. Okay. Now at the ith element, if it is we will pop all these number that is greater than ith numbers. Okay. So what I'm going to do, like ith number, and we start popping if it's greater than, if it's greater than, if it's greater than, if it's greater than, and where I found like it is less than or equals to, we will stop here. Okay. So the jth element, jth index, we will find this way. Okay. So now we have find the jth index, and the back one will be the jth index. So I have put it like this, and if it is no element is remaining, then we will update like this. So only count into AI will be added to prefix I. Uh, so similarly goes to suffix one. You can look here. Same thing I have done, and then taking answer as this. Okay. So the answer will be uh, for I, if we assume ith index as the max side, then with prefix of I plus suffix of I minus a of I. So this will be the answer for if we assume ith index. And for all index we are going to check. So the time complexity in this case will be we are what we are doing exactly, we are only iterating over array and then taking this while loop. This while loop run at in all over into O of n times. So this also take O of n times overall. Okay. So the total time complexity will be O of n, and this will solve our problem. Okay, so let's move to the next question. Now coming to the last question, so uh, I am going to explain the logic only. The code part I will show. Okay, so there is some kind of tree, and you have to find the valid paths, count of valid paths. The valid part is defined as the only one prime number it has. So first of all, we are going to deal with the prime number. So we will make the prime sieve. Okay, prime sieve begin. So we will apply the sieve of irrational and then count like mark all these number as prime or not prime. Okay, so the first part is done. We have already marked numbers as prime or not. So now the second part will be, so what exactly we have to do? If we look here, then let's say 2 is the prime number. Okay, so we can move to 1 to 4. Okay, we can move to 1 to 2, and we can move to 4 to 1. Other than this, there is nothing we can do. Okay, we cannot go 5 to 2. We cannot go 3 to 2 because 3 is prime and 5 is prime. So basically, the uh, point lies behind. If we calculate like this, if we calculate like this, we have this side count and this side count. Okay, then what we can do? We can, let's say this is count 1 and this is count 2. So for calculating the answer for 2, because we are going to calculate at each prime numbers. We are not going to calculate at 4, 1 because they are not prime numbers. We want exactly one prime number in the valid path. So we will calculate on each prime number so that they will be valid. So for calculating at 2, we are calculating the count 1 and then count 2. Like this, there may be others branches also, and there will be count I. So let's say count 1, count 2, up to count k we can say. So these many counts, okay. So let's say there is other tree, there is other tree, there is other tree. So all these count we can get, and let's say these are count 1, count 2 to count 5. What we want exactly is the count 1 should be multiplied with all these numbers. Count 2 will be multiplied with all these numbers. Count 3 will be multiplied with all these numbers. Okay. Uh, okay. So this is count 1, this is count 2, this is count 3 or count I, this is count k. So the basic idea will be we are going to calculate count 1 into total minus count 1. Here, count 2 into total minus count 2. Like this, we are going to calculate count k. Okay, so something happen. Count k into total minus count k. So what? If we sum up this, we will get from path from this side to this side, this side to this side, and this side to this side. But we only these two paths are same from this side to this side and this side to this side. They are same. Okay, so we have to like let's say this is the total answer. Then total answer. So we will have to divide by 2. Okay, because only one side is considered unique path. The other side is going to same. Okay, so with this, we got the all the path from one subtree we can say to other subtree. Okay. One children to other children. Now considering path from this to only two, not from other children from here to here. Okay. So what this will do? This will simply will be total number of paths. Okay. So we will add this total. Okay. So this is the total number of path from this node that is a prime node. So this logic I am going to use. So for using this logic, we have to do some pre-computation because without pre-computation, we cannot know the count 1, count 2, count n. And the concept used will be rerouting concept. So the rerouting concept will be used. And I think most of you are familiar with tree rerouting. If you are not familiar, then you can read the blog or CP algorithm or somewhere else. So what I have done actually, first I have calculated the prime numbers, which is the prime one, which is not prime. And then here I am doing simple DFS and calculating the subtree. Okay. So the logic is if the number is prime, then we are making that count as a zero. Why? Because we need that kind of structure. Okay. We need that kind of thing. Okay. So if the number is prime, then we are assuming that no node in this subtree is valid. Okay. Uh, so this will be used here. Okay. So like for 3, for if we are going to calculate for 3, then 5 should return 0 because 5 is already prime and we cannot have path like this. Okay. So 5 should return 0. It should return 0 to 3. Okay. That's why I have done this. So now coming to here, if we look at uh, so I think this is pretty clear that why I have done this count 0 and then simply returning this count. So if we go to this example, then what will be the final structure if we apply it from 1? Then 5 will have 0 count, 3 will have 0 count because 3 is already prime, and then 6 have 1, and then 1 have, I guess, 1 or 3 will return 0, and this side if we go to this will have 1 and this will have 0 and 1 will have 0 because 1 will have 1. Okay, so 1 is itself prime, not prime number, so it will count 1, but other than this will return 0, this will return 0. Okay, so this will be structure after applying the first DFS. So you can see uh, all the prime numbers are uh, the count is 0 at the all the prime numbers like 2, 3, 5, the count is 0 and they are returning 0 also in the to their parents. So now coming to here, second DFS. So the main logic is the second DFS. So here I am counting what I have explained. I am counting that answer. So first I have taken the all surroundings as a total. Okay. Now for each surrounding, I am calculating the answer for that. So the total that I have, you can count I minus total minus count I. Count I into total minus count. So this is the logic. And then I am adding by 2 into answer by 2 into count. This is the total count. So we will this DFS returns something that that is total count. Okay. And then count plus 2. So this will contribute into like a path from this component to this prime numbers. So only one time. Or this will answer will contribute into this kind of path. Okay. So this is the calculation part. Now if prime number, if it u is prime number, then only I am adding into us. So that I have already explained that problem. Now what the rerouting part, how the rerouting part will be handled, like if we move from one route to another route, then how things will be updated. So if any of the numbers is prime, okay, so let's say u is the root parents and b is the child. In this DFS, we are going from u to b. So now, if u is the prime, then u will have 0, and if b is the prime, then will have 0. So let's take one by one case. So let's say u is the prime and b is prime or not, we don't know. So let's say this has some size of b and this is 0. Okay. So now if we make the b is a parent and we want to update the b size, so b side we don't be updated because u is already 0. So if we add 0, nothing will happen. And u size will not be updated because u is already prime. That's why it is 0. Okay. So it will not also update it. Okay. So the everything will remain same. Okay. So that's the logic we are not updating in case of if anything is prime. Now coming to if b is the prime. So let's say this is the size of u and this is the size of b. Okay. So this will be 0 in this case if it is prime. Then if we moving from this to this as a making b as the root, then what will happen? Uh, this size will be 0 because this is the prime numbers, and this will also not be updated because this will don't contribute anything in this side. Okay, so this will remain as the option. So in both case, we can see nothing is updated because one number is prime and they don't contribute into other numbers. So that's why we are simply doing here calling the DFS again and adding the answer into count. Okay. So that's the logic for this part. Okay, this part is done. Now coming to else part. So in the else part, we are applying the logic for rerouting. Okay. So this is the rerouting logic. You can find how we are doing rerouting. So Sj of u minus equals to Sj of b. This part will doing what? So we are subtracting the size of b into size of u. So now this will don't have this subtree size. Okay. So this subtree size it will don't have it will have this only their side. Okay. And then we are adding b to size of u. Now we will have all these as a subtree. We will have all these as a subtree. So the b will become root now. So and then undoing that after calling the DFS one, we are doing undoing all these things that we have done. So this is the rerouting concept, simple rerouting concept. So you can find it, and this will solve our problem. So yeah, so that's complete our video. Let's stop here.